Hello everyone. In this talk, I shall discuss our recent work, MaskAAE, Latent Space Optimization for Adversarial Auto-Encoders. The rise of deep neural networks has caused an impressive progress in the field of unsupervised generative modeling. GANs are the most popular deep generative frameworks because of their impressive generation quality. However, training a GAN is extremely difficult as it is susceptible to problems such as mode collapse and it is sensitive to hyperparameters. On the other hand, autoencoders with regularized latent space provides an alternate neural generative framework with the advantages of stable training, interpretable inference, and efficient sampling. Despite achieving higher likelihood scores, the images generated using AAE-based generative models are not as impressive as the ones generated using GANs. VAE is the pioneering member of this family. It assumes a Gaussian encoder, a Gaussian decoder, and a Gaussian prior. Mathematically, it optimizes elbow with conflicting terms. Later in the works, researchers have proposed several modifications to the original VAE objective. They have incorporated more expressive distributional forms and they have exploited adversarial training procedures to ensure better prior matching. However, one critical aspect seems to have remained unanswered. What is the effect of the bottleneck layer dimensionality on the generation quality? In this work, we attempt to answer this question. We begin with an interesting experiment. Where we see that for synthetic datasets, the best generation quality is achieved when the bottleneck layer dimensionality of a WAE model matches the true latent dimensionality. And for real-world datasets such as MNIST, we see that the best generation quality is achieved over a range, and outside this range, the generation quality degrades. This experiment empirically establishes the fact that the bottleneck layer dimensionality affects the generation quality. Next, we attempt to establish this fact theoretically. To begin with, we assume that nature generates data using a two-step process. In the first step, it samples a latent code, and in the second step, it maps the latent code to the data space using a nonlinear deterministic function f. F is assumed to be a Lipschitz, which indicates the robustness or the smoothness of the data generating function. And the second assumption ensures that the dimensionality of the generative latent space is minimal. To understand this better, let us consider the following example, where we assume that the distribution over the true latent space is uniform, and let us consider this following two functions f1 and f2 with same range but different domains. Now this assumption basically rejects existence of any such function f1 and ascertains that the true latent dimensionality in this example is 2. Now let us understand the requirements for good generation. In a AAE-based generative model, our objective is to maximize the likelihood of the generated data under the true data distribution, which basically translates into the following two requirements. Requirement 1 states that the reconstruction error should be minimal, and requirement 2 states that the cross entropy between the chosen prior and the aggregated posterior is minimal. Now, under the data generation hypothesis, these requirements are satisfied if and only if the assumed latent dimension m is equal to the true latent dimension n. Intuitively, when m is less than n, the reconstruction quality degrades and the model fails to satisfy requirement 1, whereas when m is greater than n, the model fails to satisfy requirement 2 because of poor distributional matching. Now that we have established theoretically that for a good generation, the bottleneck layer dimensionality must match the true latent dimensionality, how do we ensure this in practice? For this, we propose a very simple modification to AAE architecture. We introduce a trainable masking layer in the latent space, which suppresses the superfluous dimensions. The masking layer is trained to minimize the reconstruction error as well as the distributional divergence. To evaluate the efficacy of the proposed method, we consider two types of experiments. In the first experiments, we consider synthetically generated datasets. Now, here we can control, in the synthetic datasets, we can control the data generation process. As a result, we know the dimensionality of the true latent space. And as we can see, that MaskAAE model is always able to discover the true latent dimensionality when the model capacity M is greater than or equal to N. And also interestingly, beyond this point, beyond this model capacity M is equal to N, the generation quality becomes flat. On the real world datasets such as MNIST, we do not know the true latent dimensionality. However, we can see that the number of active dimensions in MaskAAE always lies in the range 10 to 14. And we can see that MaskAAE outperforms an equivalent WAE model as measured by the FID score because of its capability to suppress the spurious dimensions in the latent space. As we can see that MaskAAE outperforms the current state-of-the-art AE-based models as measured by FID score on various real-world datasets. Now, this performance boost can be attributed to the better distributional matching in the latent space. As we can see that the covariance metrics of the MaskAAE for latent codes are much more diagonal as compared to an equivalent WAE model, indicating better matching with isotropic Gaussian prior. To capture this quantitatively, we define a metric called NAC, which reports the mean absolute of diagonal entries of normalized covariance metrics. And as we can see that MaskAAE reports lesser NAC score as compared to an equivalent WAE model on real and synthetic datasets. To conclude, in this work, we analyze the effect of bottleneck layer dimensionality on the generation quality. We hypothesize data generation as a two-stage process, and under this hypothesis, we show theoretically that best data generation is possible when the bottleneck layer dimensionality matches the true latent dimension. We propose an architectural modification in AAE framework to suppress the spurious dimensions algorithmically, and we demonstrate the efficacy of the proposed model for generation tasks on real and synthetic datasets.